Welcome everyone to tonight's introduction to H-NMR, to proton spectroscopy, one of the more difficult topics in organic chemistry, where you first start out by learning how the machine works and all that complicated physics behind it. I don't care. You don't care. Let's look at what you actually have to know, what your professor is going to test you on, and we'll start from the very beginning. In case you were thrown right into it, let's take a step back and make sure that you understand exactly what you need to know, starting very simple with the H-NMR signal, with the H signal. And this specifically is referring to the types of hydrogen. When we are looking at the H-NMR machine, the non-physics component, the thing that we actually have to know for organic chemistry, is really how many different types of hydrogen atoms do I have? And can I use that information to put together a molecule just from looking at a graph that has a whole bunch of lines and peaks and things on it? When we're looking at types of hydrogen, if we have a molecule like CH4, which is just carbon and 4 hydrogen, in 3 dimensions, this molecule looks something like this. Now, if I were to draw the hydrogens in different colors, you and I can tell them apart simply because of where on the drawing I put each hydrogen. But CH4 is a 3-dimensional molecule. If I have something like this, and this is a methyl group, and I spin it and spin it and spin it, you can't tell the hydrogens apart anymore because they're all exactly the same. So when you put this into a machine, and there are thousands and thousands of molecules spinning around, the question that we're looking to ask is how many types of hydrogen will the machine recognize and spit out a different signal? So if the hydrogens are the same, if I spin the molecule and I can no longer tell them apart, it's the same type of hydrogen. So with CH4, they're all exactly the same. I have one hydrogen type, which, as we'll see after, translates to one signal on an H-NMR graph. What if I crank it up a bit and do a molecule like this? Ethane. How many hydrogen types would you expect on a molecule like ethane? Well, let's see what we have. Ethane is F2 carbons. So if I draw them out, I have this. And how many hydrogens? 1, 2, 3, 1, 2, 3. What I'm looking at here is if I have an sp3 hybridized carbon atom and it can spin, any hydrogen on that sp3 atom is going to be exactly the same, just like we saw with methane. And looking at it with ethane, that means each of these are exactly the same and each of these are exactly the same. But there's one more thing I want to look at. So rule number 1 is hydrogen on an sp3 carbon are going to be exactly the same. The second thing you want to look for is symmetry. If I have a plane of symmetry going down the middle of the molecule, that means I take this molecule and then I flip it. If I turn it sideways, where the red become the green and the green become the red, it still looks exactly the same. And that means I have just one hydrogen type once again. And that means the H-NMR graph is going to have one signal. If you're with me so far, let me see a couple of thumbs up in the comments. Again, we're starting very simple, but we're going to build up the complexity to make sure that you're crystal clear on this information. I see, makes so much sense, unlike my professor. Well, a lot of professors are not necessarily cut out for teaching. And part of it, I think, is because they don't like to. But you're here, and I love this material. So hopefully, as this gets more complicated, you'll be able to really understand and follow along. So let's jump to a more complex molecule. What if I take my carbon chain, and this time I make it 4 carbons long? You know what? Let's keep it just like this. 4 carbons long. So I have my CH3 at the end. And then here I have a CH2. Here I have a CH2. and here I have another CH3. For each carbon, I find it helpful when you look at the hydrogens as their own thing. That's why I put them in different colors. But let's take a look. Let's first validate the fact that this is an sp3 carbon atom. All the hydrogens on it are going to be equivalent. That means I have one type here that is blue. If I then look over at this one right here, because this is a CH2 and this is a CH3, they are very obviously different. They are no longer the same hydrogen type, meaning I can close my eyes, flip the molecule, open my eyes, and I can still tell them apart. That gives me a second hydrogen type and therefore a second signal. If I look over and I see another CH2, I notice that this can potentially be unique. And then if I look over to the left once again, potentially unique. But don't forget, we have symmetry going down the middle. The right half and the left half of the molecule are exactly the same. And that means where I have a CH2 here that is different from the CH3, this is the same as this CH2 over here. It is the same thing on either side because of symmetry. So that means together, these two are going to give me just one signal between them. And the same thing for the CH3 and the CH3. Because of symmetry, the CH3 on the right is no different than the CH3 on the left, and that is going to give me one signal for a total of two hydrogen types here. And therefore, we have two signals. If you're with me here so far, put harder in the comments and we'll crank it up a notch by doing two things. First, you're not going to get your molecules this cleanly written out with all the hydrogens visible. You're going to get something more like this. Line structure, and now you're told find the hydrogen type. So let's actually not quite make it as let's not make it as difficult yet. Let's look at this right here, which you'll notice is the same thing as what I have here, but suddenly it's less obvious. Let's make it bigger. And so if you see something like this on your exam, here is how I recommend breaking it down. First, I like to mark the carbon atoms, either by drawing in quick hydrogens if I'm trying to count, or just putting a circle to say, hey, this is a unique carbon atom. I notice that this is a linear molecule with symmetry down the middle. So I recognize that this is also a CH3, same exact. And then I see that I have a CH2 here, which is the same as the CH2 here. And once again, I get my two signals. Now, what if I take the same molecule, but this time I add a halogen to it? For example, a bromine. How many hydrogen types, and therefore how many signals do you see on the molecule once I cranked it up a notch? Because of the bromine, I no longer have symmetry down the middle. That means the right and left half of the molecule are different. And so if I have a CH3 over here, that is going to be very different from the CH3 over here. And the way I want you to think of it is it's not just about what I see, it's about what I have next to it. So this is a CH3 that is next to a bromine. This is a CH3 that is not next to a bromine. And the way the H-NMR machine works is that the electronegativity of the nearby atoms will pull on the hydrogens a little bit. Again, we're not going into the physics behind it, but I'm sharing enough for you to be able to understand why there are differences and therefore be able to easily tell them apart. So the fact that I have no symmetry, the two methyl groups are different, but also every group on the chain is going to be different. And so if you correctly put 4 in the comments, absolutely right. Because I also have a CH2 here, and I have a CH here. That means I have 4 hydrogen types, and that means 4 signals. What if I look at something like a ring? So let's say I have a molecule that looks like this. We'll put a carboxylic acid there. How many hydrogen types am I looking at now? And therefore, how many signals? To figure out how many hydrogen types, first we want to identify all the hydrogens. So let's change the carboxylic acid. That is 1. For something like this, instead of just circling the carbon, I sometimes like to write a little line. You don't necessarily have to draw the hydrogen, but just kind of mark it so you know what you have. So I have this hydrogen here sitting on a carbon next to a carboxylic acid. Next to that, I have a hydrogen that is sitting on the carbon that is next to a carboxylic acid, so that's different. And then over here, I have the hydrogen that is sitting on a carbon that is exactly across from that carboxylic acid. So that gives me a couple of different hydrogen types. And then if I continue going here, these are no longer unique because remember, symmetry in the molecule. And if I have symmetry in the molecule, whatever I have at the top, I have at the bottom. That means the purple one is repeated, the light blue one is repeated. And I have a total of, once again, 4 hydrogen types. And that means I have 4 singles. All right, if you are confident with hydrogen types, let me know in the comments that you are ready to move on to something more complicated. If you're just joining or watching the recording, welcome. For a copy of tonight's session notes, make sure you sign up at layoversi.com/orgolive. Additionally, for more practice, because today is just an introduction, we're going with the basics. For more advanced practice on spectroscopy, make sure you try the worksheet that I have not available on my website. Just put worksheet in the comments and I will give you a link to download it so that you can do even more practice on NMR. Just put worksheet in the comments, even if you're watching the recording. So we have the basics, but what do we do with this information? This is what you came here to learn tonight, right? The H-NMR graph, and specifically what it is that we're looking on this graph. So when you look at H-NMR, you're going to see a line with numbers anywhere from 0 to 13, and you'll see some lines like this, and like this, and like that. What do all these things actually mean? And what are we going to do with this information? So we can go into the complicated, break it all down crazy science. I don't care about that. You don't care about that. What is the tactical? What do you need to take away from here so that when you see a problem on your exam, you'll be able to solve it? That is what I want to look at with you. That is what I want to focus on. So the first thing we're going to look at is the splitting patterns. And we'll look at the common ones that you're going to see. I want you to look for the logic in the way that these things are named. If I have a single peak, just one peak going up, this is called a singlet. Logically, that makes sense. If I have 2 bumps on my peak, this is called a doublet. If I have 3, following the same pattern, you should know at this point it is called a triplet. If we have 4, quartet. If we have 5, this is a quintet. Once you get past 5, they tend to get lazy. And so I have seen sextet and septet, but typically they'll just draw something really messy and call it a multiplet. And the multiplet, depending on your professor, is going to be anything greater than or equal to 5 peaks. It's just got multi. It's got a lot. Okay, but what does all this actually mean? And more importantly, what are we going to do with this information? Let's take a step back and look at one hydrogen on a molecule. We have some complicated molecule, whatever it is that we don't care about. And there happens to be one hydrogen atom over here. This hydrogen atom, if it was all by itself, would have a single peak. It would look like that. But every time this hydrogen has a neighbor, the neighbor and its electrical field is going to impact that hydrogen and try to pull it in another direction. The neighbors are going to pull it in different directions and try to split it. So if I take this thing and I start pulling at it and pulling at it, then the signal is going to break up And now I have 2 peaks. So what we're looking at here is this is the peak that I'm starting with. And this one, because it has one neighbor, it got broken into one extra peak. So what the neighbor does is it's not every bump means a neighbor. It's every additional bump after the initial peak that is an additional neighbor. If I take my peak and now I have a neighbor pulling it on one side and pulling it on the other side. So this is N1, N2. I have 2 neighbors. These 2 neighbors are going to split this into a total of 3 because I have my initial peak and then 2 neighbors pulling it in either direction. If that makes sense, put an N in the comment for neighbors. And what we're going to look at now is the formula to calculate it. And the formula is very simple. You don't have a lot of math in organic chemistry. That formula is as follows. The number of peaks is equal to N plus 1, where N is going to give me the number of neighbors, plus 1, where that 1 is my initial peak. Very simple, I hope. So let's work backwards and see if we can fill in what all of these mean. So with these splitting patterns, how many neighbors do I have for each of these that I have here? If N plus 1 is going to give me the neighbors, then if I look at this, all I have to do is ask myself, what do I see? Minus 1 is how many neighbors I have. This singlet right here is not being pulled in any direction. That means it has no neighbors. I see a total of 1 bump. 1 minus 1 is equal to 0 neighbors. If I go down to the doublet, then I see a total of 2 bumps. That's 2 minus 1 is 1 neighbor. I had my initial peak, the neighbor broke it in half, and that's how I got 2. For the triplet, I see 1, 2, 3. 3 minus 1 is 2 neighbors. Quartet, 4 minus 1 is 3 neighbors. 5 minus 1 is 4 neighbors. And a multiplet is m minus 1 equals whatever number it is that we have. So that part was the easy part. But enough hypothetical. What does this actually look like on a molecule? So we're not yet going to look at a graph. I just want to look at a molecule with neighbors. If I have, let's go with ethanol. It's a small, simple molecule. 2 carbon atoms. And if I draw it out, then I have my 3 hydrogens on the methyl group at the end. So that'll be carbon 2, I guess, because the 1 would have to be the one that has the OH on it. And then we have 2 hydrogen atoms right over here. So let's start with the green one. The green hydrogens, because they're all the same, will have 1 signal for all of the green. And it would start out looking like this, except how many neighbors does it have? I have 1, 2. Now here's where it gets a little complicated. Even though the blue hydrogens are exactly the same and make for 1 signal, the fact is, as neighbors to the green, even though you can't tell them apart, we still know that they're 2. So it says if your neighbors are identical twins, you don't know which is which, but you know that there are 2 because you can see that there's 2 of them. And in this case, because we have plus 2 neighbors, we're going to get a peak that has a total of 1 starting peak plus the 2 neighbors for a total of 3. And that means the green peak is going to give me a triplet for the CH3. Then if I look at the CH2 group over here, I start out with 1 peak for the light blue, plus how many neighbors do I have? When we're looking at a neighbor, it's hydrogen sitting directly on a carbon, nothing else. So this hydrogen here is not neighbor to anything else because it's not sitting directly on a carbon and it's not on the next atom. There's an oxygen in between, so we're not going to count it. The only neighbors that I have for the light blue hydrogen are 3 green hydrogen. That means I have a total of 3 neighbors, giving me my starting peak plus 3 neighbors for a total of 4. That would give me a quartet. And then, let's change the color here. The alcohol, because the hydrogen is sitting on an oxygen, it has 0 neighbors, and that just gives me a tiny little singlet. So the clue for an alcohol is you have a tiny, kind of broadish singlet, and I think one of the examples I have prepared has an alcohol in it. If you're with me, say yes in the comments. I want to make sure that this is clear, going from the molecule to figuring out what kind of peaks, what kind of bumps we're going to see on the graph. Should we do another one or jump into more complicated? All right, let's try another one. So tell me how many hydrogen types you expect to see on this molecule, and then we'll look at what kind of peaks we have for each of them. So how many hydrogen types? Let's start with the carbon on the right and work our way this way. The carbon on the right is a methyl group. Let's make this molecule bigger, first of all, and then let's mark it up in color. So we'll start with a methyl group over here. That's a CH3, and I'll draw 3 lines to show that I have my 3 hydrogen atoms. It starts out as what would be a singlet, plus I need my neighbors. How many neighbors do I have? Well, the carbon 1 over has 2 hydrogens, and we have no other neighbors. So that means 2 neighbors plus the 1. My green is going to be a triplet. Next, we'll look at the light blue. We have the 2 hydrogens. We already know that these 2 are neighbors, so that is 3. We start with our singlet. And you don't do this, by the way, on your exam. You go straight to this. I'm showing you how I'm coming up with it so that you can build up the peaks with me. The neighbors that we have are 3 on the right for the green. This carbon here does not have any hydrogen, therefore no neighbors, and we only have the 3 green for a total of 4. 3 plus 1 and plus 1 is 4. I get a quartet. And then if I look all the way to the left, that's 3 hydrogens there. But the only neighbor I have is a carbon with no hydrogens, and that means it's going to be a singlet plus 0 neighbors for a singlet. And these are the 3 peaks that I would expect to see on a graph for this molecule. So we have the peaks. Are you ready to put it together? If you are, let me see a fire emoji in the comments. All right, I'm seeing the fire come in. Oh, I was going to grab a table. Let me think. How do I get a table onto the notes? I totally forgot to grab one. You know what? I'm just going to have to draw it out because I forgot to grab it. When you are studying this topic on your exam, what you're going to see is some kind of table or chart that looks like this. And let me know if you have seen something like this, or worse, if you had to memorize it. And it's got the numbers. And then you have this functional group here, and this functional group here, and this functional group, and this functional group. And what these represent is the ranges, where if I have this functional group here, then it'll show up on the graph from this number to this number. And if I have this functional group here, it'll show up on the graph from this number to this number. And worse, you actually are told to memorize it all. So you're looking at it and all you see is a mess of numbers with no idea what on earth you're going to do with all of that. This is what I had to do. And let me tell you, it doesn't work. It's too overwhelming. It's too complicated. So we're not going to do that. Instead, what I want you to do is look at the general idea of what is going on, the general range of the numbers you have, the groups that you have. And if you can learn to recognize it, you do not have to memorize it. So what does that mean? Well, let's look at the graph the way that makes more sense. Let's look at it more logically. The graph for H-NMR is going to range from 0 all the way till about 13, depending on what your molecule is, because sometimes you're not given all the numbers. So we'll draw it in. I'm just going to put ... because I clearly ran out of room with the numbers. And the next thing I want you to look at is forget the specific numbers. I want you to think of this end of the graph as boring and this end as exciting. The more exciting the group next to your hydrogen, the more it's going to shift it all the way to the exciting side. And the less you have going on the molecule, the more it's going to shift over to the boring side. And with that in mind, here are the major groups that you are going to see when you're looking at graphs. If you have just carbon and hydrogen, it's going to show up around here, around the 0 to 1 range, depending on if it's a methyl, an ethyl, and not a lot more going on next to it. For example, just a long carbon chain or a branch on something that doesn't have anything exciting. But if I add something exciting onto it, for example, a halogen, that will typically show up between, say, 2 to 4. And it's not the halogen that we're looking at. It's the carbon, or rather the hydrogen, that is sitting on the carbon that is holding your halogen, for example. So that hydrogen being so close to a halogen is slightly more exciting than a hydrogen just sitting on a carbon with nothing else. If I have something a little bit more electronegative, that'll show up here. Not necessarily more electronegative, but more exciting, more powerful in terms of being able to pull electronegativity away from that hydrogen. It'll be ever so slightly shifted over. That will be an oxygen or a nitrogen. And these are a lot of your plain molecules, your alcohols, your amines, your halogens. The next level of excitement is if I add a pi bond into the molecule. A pi bond by itself, for example, a double bond will show up in the 5 to 6 range. If I add in something like an aromatic ring, that typically shows up around 7, depending on what else is on the ring. So that's the hydrogen on the aromatic ring. And then all the way to the left is where I have my hydrogen sitting on an aldehyde or a carboxylic acid. So these will typically show up between 9 to 11. So if I have my aldehyde or my carboxylic acid, these are very, very exciting hydrogens. And notice, that doesn't look like a hydrogen. Let's try that again. And notice that it's, what am I doing? I'm trying to make it purple. There we go. Notice that it showed up all the way to the left of the molecule. Now, I called it boring and exciting, but what specifically are we looking at here? This is the chemical shift. And what this tells us is if I know I have 2 hydrogens with 3 neighbors and they're shifted this far on the graph, they should be part of whatever kind of molecule. So let me know if this makes sense and you want to see this applied rather than straight up memorization. Put practice in the comments and we'll work through some practice problems to actually bring this to life so that you can see how to break down the graph. Now, because this is an introduction to NMR, we'll go easy here. But if you are comfortable with what we're doing here and you want to practice even more difficult molecules, even more difficult graphs, make sure to try the NMR worksheet that I mentioned before. It's not available on my website. Just comment worksheet and I'll send you the link, and that way you can continue to practice. So for our first molecule, we'll look at a graph like this. And what I'm looking at here is less of this is very complicated, let's figure it out, and more how do we approach something like this? We're given that the formula is C5H10O. And on this graph, we have starting at 0, 1, 2, and 3. So as you can see, this is all pretty boring. And what are the peaks that we have? I'll draw them in different colors so that we can make this molecule, treat it like a puzzle and bring it together. Just under 1, I have a 3-hydrogen triplet. Just after 1.5, I have a 2-hydrogen, 1, 2, 3. It almost looks like a multiplet. So we'll put it over here. Sometimes they're hard to read, so you may see it expanded or see something written next to it. Just past the 2, we have a 3-hydrogen singlet. And our last peak on this molecule is a 2-hydrogen triplet a little bit past that. All right, here we go. You're given this graph, you're given a formula. Where do you start? How do you approach something like this? The first thing is not to look at the graph at all. The first thing is I need to know, do I have any rings? Do I have any pi bonds? Do I have any complicated functional groups that I need to account for? And for that, I'm going to use the index of hydrogen deficiency equation, which I have a video linked in the description. And that is CnH2n plus 2. The oxygen does not change the count, so we're not going to account for it in the formula. We have 5 is N because we have 5 carbon atoms. That means that 2N plus 2 is 2 times 5, which is 10, plus 2 is equal to 12. I should have a total of 12 hydrogens if the molecule was fully saturated, but I only have 10. That means I'm missing 2 hydrogens, and every degree of deficiency is a cost of 2 hydrogens. That means I have 1 degree of unsaturation. I have 1 pi bond, 1 pi, or 1 ring. And now I have to consider, is it a pi bond or is it a ring? And where does it occur on the molecule? And how do I account for it? The next thing I like to do is I'm kind of going to start guessing a little bit because the molecule is small enough. I could take the time to just draw out all the constitutional isomers and probably come up with something. But instead of doing that, I'm just going to reason, would it more likely be a pi bond or a ring? Well, let's see what we have. If I have 5 carbon atoms and I only have 4 peaks on here, then I have 2 options that it could be one of 2 things. It could either be that 2 of the carbons are exactly the same and therefore they're showing up as 1 peak, meaning some kind of symmetry, or one of the carbon atoms does not have hydrogen on it. So these aren't representing carbon atoms, these are hydrogens, but the hydrogens sit on a carbon. So if I have 3 hydrogens, then this is probably a CH3, 3 hydrogens sitting on a carbon. 2 hydrogens would be a CH2. 3 hydrogens would be a CH3. And 2 hydrogens, once again, would be a CH2. If I count all this up, I have accounted for on this graph a total of 4 carbon atoms and 3, 6, 8, 10 hydrogen. That means all I'm missing from my original formula of C5H10O is a carbon and an oxygen. And with this in mind, I'm going to guess that that carbon and oxygen is probably where my pi bond is located. It's probably a C double bound O, and that lets me have all these pieces. So now all I have is a puzzle. I have a C double bound O, I have a CH2, a CH3, a CH2, and a CH3. So let's put this somewhere over here. And now we're going to use the graph to figure out how to put all of it together. Let's start with the CH3. If this CH3 is a triplet, that means how many neighbors does the CH3 have? Remember, every peak starts out as 1, and then neighbors pull it apart. So if I count the tips and then I subtract 1, that's how many neighbors. This triplet has 2 neighbors. So if I have the CH3 at the end of the molecule, I like to do my ghosts in gray. Ghost meaning I don't know what this is, but I know that there's going to be a CH2 right here. And the question is, given that I have 2, is it the dark blue or the light blue? Did not mean to make them both blue, but so we have. So I know that there's a CH2 next to it. If I look over at this CH2 over here, it's a multiplet, and it looks like it has a total of 6 tips. That would be 1, 2, 3, 4, 5, 6. The 2 on the right and left are very hard to read, but it's obvious enough if we count it. That means these 2 hydrogens have 6 minus 1, which is 5 neighbors. How can a CH2 possibly have 5 neighbors? It has a CH3 on one side, and then it has a CH2 on the other side. So we know that this is going to have a CH3 and a CH2. That means the CH2s are next to each other. And so we don't yet know which is which, but we know that both of the CH2s are accounted for. That's supposed to be a 2. And this is the one that's specifically attached to a CH3. Well, if the dark blue is attached to a CH3, then this is going to be my dark blue CH2. Then this is probably the light blue. Let's see if we can justify it by looking at what we have. If I have a triplet, 1, 2, 3, that means it only has 2 neighbors. 3 minus 2. Sorry, 3 minus 1 gives me 2. That's how I got my 2 neighbors. And can we say that if this has only 2 neighbors, the 2 neighbors would be a CH2? Well, we know that the CH2 is attached to the CH2. So the 2 neighbors are right here. This CH2 has 2 neighbors. This CH2 has 5 neighbors. That's how we know the colors are correct. And then the last peak on the graph here is the 3 hydrogens. The 3 hydrogens are showing up as a singlet, just one tall peak. That means they have no neighbors. They're sitting at the end of the molecule completely isolated. There's no carbon hydrogen touching it. Well, what is a way to isolate, to make sure that they don't have neighbors? Well, just put the carbonyl in right there. And that is our entire molecule. Everything is put together. You want to take it a step further and justify. So we figured this out based on just the number of neighbors and the splitting patterns, but I also want you to look at the chemical shift. I called this on the right the boring region. Notice that the CH3 is boring because all it has is a CH2 next to it and another CH2 next to it. That is what I mean by boring. There's nothing going on next to that CH3. The CH2, the dark blue one, is slightly more towards the exciting region, but it's still pretty boring. And why is this one still pretty boring? Because all it has is a methyl and a CH2 next to it. But if I go to the light blue CH2, this one is the most exciting group on the molecule. It's the most shifted. It's got the most chemical shift. It's most leftmost. It's leftmost. And the reason for that is look what it has. This CH2 is bound to a carbonyl and bound to a CH2. And the most exciting thing on this molecule is the carbonyl. So if this is bound to the most exciting thing and has another neighbor, of course it's the most exciting group. So we're validating that. We're justifying it. And then the CH3 is also next to the most exciting group. That's why it is also towards the left. But it has no other neighbors. So it is less exciting than just the CH2, which is why it's not as shifted to the left. Now that we have all the puzzle pieces together, your professors probably don't want it like this. They want you to draw a molecule. So we'll number it 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, where carbon 2 has a carbonyl, and that's our final product. Question: how do we know whether the signals are CH2, CH3, etc.? In this example, and for many students, you're going to get the information right here. So this problem had the 3H, the 2H, the 2H listed out like that. Sometimes you'll see an integration value, something that looks like that, showing you how high it is relative to another peak. If that is something you learn, you will learn the math behind it. I learned that way back in the day, but most of my students don't, so I don't teach it. And sometimes you're not given anything at all, and you just have to guess based on putting the math together. So in a situation like that, you would say, this is a triplet. What does that mean? It has 2 neighbors. Okay, so I know this unknown group has 3 neighbors. And then this is a singlet. I don't know how many hydrogens, but this unknown group has no neighbors. And then the pieces will come together not as quickly, but they will still come together. So Joshua, let me know if that answered your question, because that is a very, very good question. Forgot to put that up. All right. So if you're with me so far, and if this example here helped clarify something, let me see. What have we not used yet? What emojis are available? Let me see a hand emoji in the comments, and we'll do another one. What should we do for the next one? Joshua, let's try one where I don't give you the hydrogens, just so you can see what I'm talking about. And we'll use that as our next example. And I see the hands coming in, so excellent. For this example, we will have our graph. And on the graph, why did I not think to make this bigger? I can't see anything. On this graph, we have a singlet, which I'll draw in purple. Actually, I'll put the numbers in after. So we have a singlet all the way to the left. And then at around, just at around 1, we have a, oh my goodness, I can't see what I have there, a triplet. So we'll make that 0, 1, 2, 3, dot, 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 and I'll make this 12 because the graph jumps all the way. And then I have a quartet that is sitting around 2. These are not drawn to scale, so we're not going to go with my heights and say, oh, that's higher or lower. This is just happens to be how I drew it. And now let's figure out how to put this together, given a molecular formula of C3, H, 1, 2, 3, 4, 5, 6, O2. Okay, so this is what we're given. Not a lot of information, which is going to make it more difficult. So let's see how to approach this. First thing, index of hydrogen deficiency. We want Cn H2n plus 2. N is the number of carbon atoms. That is 3. So that means 2n plus 2 is going to be 2 times 3, which is 6, plus 2 is equal to 8. I only have 6. 8 minus 6 is 2. Divided by 2, I have 1 degree of hydrogen deficiency. Let's move this over so that we're not crowded here. This molecule is going to have 1 pi or ring. As you do more and more problems, you're going to notice some patterns, and here's a pattern I want you to look for. If you see an index of hydrogen deficiency, so this is the clue that you're looking for. You have an index of hydrogen deficiency is equal to 1, or you have more things on the molecule, but if you have at least 1 pi bond or ring, and you have 2 oxygen, I want you to look at 10 plus. Notice that we have a peak at 12. That right there is your clue that we have a carboxylic acid. How do I know it's a carboxylic acid? The index of hydrogen deficiency is the pi bond between the carbon and oxygen. The 2 oxygen is 1 on the carbonyl and 1 on the OH. And the 10 plus is that hydrogen that is very, very exciting. Recognizing that, the entire molecule just fell into place. So let me know if you looked at this to start and you weren't sure if it was easy or hard. And then you're looking at it now and you realize, oh, this is not a hard molecule at all because of this trick. That is one step. You'll be faster on your exam. And as you go through my examples, you'll see that I have a lot of different shortcuts that just make everything fall into place. You are so, so very welcome. And I hope this is part of it. So let's see what we have. If we have 3 carbon atoms and we have 3 signals, then we automatically know that these 3 signals represent the 3 carbons on my molecule. I don't know how many hydrogens, but I know I have a purple one, I know I have a blue one, and I know I have a green one. Having immediately recognized what is going on here, I know that this right here is my carbonyl, my carboxylic acid specifically. And that means I have 5 hydrogens left between the blue and the green carbon. I don't know how many on each, so let's look at the clues. If the green carbon is a triplet, that means 3 tips, 3 peaks on here. That's a triplet. 3 minus 1 is 2. I have 2 neighbors. So I don't yet know what is on this thing, but I know that whatever is next to it is probably a CH2. And since the only carbon available in this case is this one, this is probably a CH2. Now let's see what the blue one is. If the blue one is a quartet, that is 4. 4 minus 1 is 3. That means the blue one has 3 neighbors. I don't yet know what this is, but I do know that it's going to be next to a CH3. So is this right here a CH3? Yes, it is, because I have nothing else. Now here is another shortcut I want you to recognize. Anytime you have a quartet and a triplet, 3 hydrogens and 2 hydrogens, they are the neighbors to each other, CH3, CH2, that is an ethyl group. So this right here is another shortcut that will make your life a lot simpler. Recognize a triplet and a quartet. When you have the triplet that is a CH3 and the quartet as a CH2, that is an ethyl, and that is one more group that you instantly recognize on the molecule. And that is it. So with a bigger molecule, I like to do a more step-by-step mathematical accounting. We don't need it here because it's obvious, but I want to do it just to show you so that when you do the more complicated example, you'll know what to do. So we'll take our C3H6O2, and we'll start with the first group. Let's pretend that this is a very complicated molecule and we're trying to figure out what is left. The first group we accounted for was the carboxylic acid, which is 1 carbon, 2 oxygen, 1 hydrogen. What does that leave me with? A C2, H5, and nothing else. And then I can account for these 2 groups separately, or I can say, hey, I found an ethyl group, which is a CH3 and a CH2. That is C2H5. I got nothing left. My molecule is good to go. I have my carboxylic acid. Attached to that, I have my blue group. And I know that the blue is attached to the purple because it's the most exciting, and this is the exciting group. So the one that's closest to it, more shifted on the graph, is closer to it on the molecule. We know that this is a CH2. And then towards the end, because terminal groups like methyl groups tend to be less exciting because they're on the end of the molecule, that's my green one. That's a CH3. That's my molecule. And if I want to redraw it, I will draw it like this. 1, 2, 3. And there we go. In the comments, was this easy, medium, or hard? And is this what you expected when you first saw the example? I see easy and medium. Well, hopefully something like this is easy by the time you practice this a few times. It starts out difficult because of everything going on, but I want this to become easy for you as you really break it down and understand. So yeah, that's what I'm looking for. With practice, it'll become easier. Excellent. Let's try another one. And for this one, once again, I'm not going to give you hydrogen numbers, so we'll have to kind of guess at what we have. And on this graph, we're looking from 0, 1, 2, 3. So again, kind of boring. The peaks on this graph include just after 1, I have a triplet. Just after 2, I have a singlet. And a little bit beyond that, I have purple and let's go with blue next. I have a quartet. Okay. So this is all we're given and a formula. The formula is C4 H8O. All right, so at this point, no matter how comfortable or not comfortable you feel about this, you should know the first step, index of hydrogen deficiency. In the past 2 examples, I wrote it out, but as you get more comfortable, here's how I want you to be able to do it on your exam. You just look at it, you say C, N, H2N plus 2, N is equal to 4, so all I'm going to do is 2 times 4 is 8, plus 2 is 10, minus 8. That's 2 over 2 equals 1 degree. So I have 1 pi. 1 degree is equal to 1 pi or 1 ring. I have a total of 4 carbons and 3 signals. So it's probably not a ring because rings tend to have some kind of symmetry or something else going on, but let's see. These are probably representing a carbon with some number of hydrogen, carbon with some number of hydrogen, carbon with some number of hydrogen. That means I have a carbon with no hydrogen on it because I don't have a signal for the 4th one. Okay, so let's take the information we see and put it together. I'll start with this one right here. The fact that this is a singlet, it means it has no neighbors, nothing to split it. And the only way to have no neighbors is if the thing next to it has no hydrogen or, yeah, has no hydrogen. And so that means that this carbon with no neighbors is very likely attached to the orange one. And the only way for that orange one to not have a signal and not give this one any neighbors is probably a carbonyl. That's where the oxygen is accounted for. So I have 2 of them. And then I could go through all the steps for this, or I can recognize a pattern. I have a quartet and a triplet. A quartet and a triplet, and only 2 carbon with hydrogen groups remaining on my molecule, it has to be an ethyl group because what else can it be? Quartet, triplet, that is an ethyl group. So let's go through it and show how we got that. I want you to recognize it, but I'm showing you in case you didn't see it. If I have 4 on a quartet, 4 tips, that means 4 minus 1 is 3 neighbors. So whatever this is attached to is probably a CH3. And then if I look over at the green one, I have 1, 2, 3. 3 minus 1 is 2 neighbors. Whatever is attached to is probably a CH2. Given that I have nothing else available on my molecule, this one is not a neighbor. It does not have any neighbors, nothing to split it. That means the only thing that could split this is this. If the blue has a neighbor and the green has a neighbor and no one else has neighbors, they have to be each other's neighbors because there's no one else to neighbor. And so if the blue has to have a neighbor and the green has to have a neighbor, they are each other's neighbors. That means the blue is going to be the CH2. The green is going to be the CH3. So we'll draw in the CH2 here. The green is the CH3. And then this being a singlet all the way on the end of the molecule, it has to be a methyl group. It has to be a terminal group. Otherwise, the molecule would continue. Let's justify the chemical shift. The methyl furthest away from everything is boring, so it's all the way to the right. The carbonyl is holding on to purple and blue, so those would be more exciting, more to the left, purple and blue. And if we have something near an exciting group and near something else, that's more exciting than if it's just a methyl group near the carbonyl and nothing else, which is why the methyl tends not to be your most exciting. The internal group tends to be more exciting. And so our final molecule, so Joshua, again, based on your question before, how do we know if nothing is given? We kind of figured it out backwards, but we came up with our structure. So we have 1, 2, 3, 4 carbons on the molecule, 1, 2, 3, 4, with a carbonyl sitting right over there at position number 2. I think you switched the CH3 and the CH2. Let's see. If this right here has 2 neighbors, the green is my CH3, right? 2 neighbors means that the CH3 has a CH2 neighbor. If this right here has 3 neighbors, that means the CH3 is the neighbor. This is the CH2. What did I switch? I'm not sure. Let me know if I'm missing something or if it clarified your question, because I'm not sure. Can you choose something with coupling, like doublet or if you mean like a doublet of doublets, I'm not going to go into that today because today is an introduction to NMR. And I don't know that I actually ever taught that. So that is kind of at a higher level. A lot of professors do require it, but most don't. So yeah, I have not covered that. For even more practice, make sure to try the NMR practice worksheet that I mentioned earlier. Just comment worksheet and I will give you a link. Then for a copy of tonight's session notes, along with the session notes for all the past workshops that I've done, all the past live streams, just go to leahforsci.com/WorkGoLive, sign up there. You'll get the notes, old worksheets, and so much more.